In the distillation, difference in volatilities is used in the separation of two or more components from their miscible mixtures. The term relative volatility, which is worked out from the experiments and available as vapor-liquid equilibrium data. Higher the relative volatility, easier will be the separation of two components from their mixture using distillation process and vice versa. Fluid nature, operational requirements, economics, etc. affects the selection of type of distillation column internals, viz. packing or trays. These internals are provided to ensure proper contact of uprising vapors and downflowing liquids. Overall distillation system contains various components like feed preheater, distillation column, condenser, reboiler, etc. Knowledge of complete distillation system along with column internals is required to design and operate it more efficiently. Distillation is a process for the separation of two or more components of desired composition from their miscible liquid mixtures. Like every separation technique which uses the difference in properties of two components, e.g. density difference used in the liquid-solid separation from their slurry by gravity settling method, difference in volatility of two components is used for their separation using distillation method. Being one component is more volatile than the other in their binary mixture, on heating liquid boils and generates vapors which are also a mixture of both the components but with relatively higher concentration of more volatile components, as observed experimentally. As shown in the Fig. Point 1, A is relatively more volatile than B. Though vapors generated are enriched with high volatile trays are relatively complex distillation internals from a design and hydraulic standpoint, which consist of a tray deck, downcomer, and outlet weir. In the operation of a typical cross-flow tray, liquid enters the tray at one side and flows across the tray toward a downcomer at the opposite side of the tray. Bruckert, 1968. As the liquid flows across the tray, vapor passing through the perforations in the tray surface forms a froth on the tray surface, which allows mass transfer to take place. At the outlet from the tray, the froth spills over a weir subtending the tray into the downcomer. The downcomer is a device for transferring the liquid phase downward to the next successive tray but is sealed by such liquid against the vapor passage upward. In the downcomer, the vapor separates from the froth, leaving a pool of disengaged liquid in the downcomer below the level of the active tray surface. The disengaged liquid enters the next tray under the force of its hydrostatic head, independently of the forces that create the froth and move the froth across the tray. The tray decks commonly used in refinery and petrochemical plants can be divided into three types: sieve, valve, and bubble cap. Bubble cap trays, which were patented by Cellier Blumenthal in 1815, were the most popular type of trays before the 1960s, when they were replaced with new designs of sieve and valve trays that matched the performance of bubble cap trays but were much cheaper to install. Kister, 1992. Currently, bubble cap trays are used only for special applications. Sieve trays, which are perforated thin plates, are very good in fouling applications or when there are solids present because they are easy to lean. However, the turn down, the performance when operating below the designed flow rate, is relatively poor. Wonkit, 2012. Valve trays are designed to have better turn down properties than sieve trays. Therefore, they are more flexible when the feed rate varies. Although tray columns provide stepwise contact between the vapor and liquid phases, packed columns provide continuous contact without full disengagement of the vapor and liquid between the top and bottom of the packed bed. Pilling and Holden, 2009. In a packed column, the liquid driven by gravity flows down the mass transfer zone comprising the random and / or structured packings in the form of a trickle film or falling droplets, while the vapor as the continuous phase flows upwards from the bottom to the top of the column. Makowiak and Makoyak, 2014. Packings are generally divided into random and structured packings, which can be made from different materials, such as metal, plastic, and ceramics. Figure 2.1 shows the history of the development of characteristic random packings of different generations. Regarding the structured packings, they can be classified into sheet, gauze, and grid packings. Spiegel and Duss, 2014. The main advantage of structured packings is their relatively low pressure drop per theoretical plate or equilibrium stage, which makes them the most effective vapor-liquid contactor for low pressure, mainly vacuum applications, Oluyik 2014. Packing with a pressure drop that is about 1/5 that of the trays, Lockett, 1986, is often the preferred choice in cases where a pressure drop is the overriding consideration, such as vacuum distillation or where vapor recompression, heat pumping, is used. The two features that should be maximized in pack beds are the open area, which is the average percent of the cross-sectional area of the column not blocked by the packing, and hence available for the flow of vapor and liquid,